this lesson, I wanted to show you an example of a problem where we're dealing with a weak base rather than a weak acid. When we write a formula for ionization of a weak base in water, we show the base ionizing a water molecule. So the base takes a hydrogen ion away from a water molecule, leaving hydroxide behind. So the transfer of hydrogen happens from the water to the base. So water's acting as the acid. In the KB expression, we don't include water, since water is a liquid, but we do include the other species in the reaction. So if we take a look at the question I've got here, it says, if the pH of a pyridine solution is 8.5, what is the concentration of pyridine in that solution? The Kb for pyridine is given here is 1.7 times 10 to minus 9. There's a couple things that I like about this example. This one's a little different in what it's solving for. It gives you the pH, it gives you the Ka, and we're actually looking for the initial concentration, which hasn't been the case before. So that's something that will be nice for us to look at. And the other thing is, I wanted to show you that if you know that pyridine is a base, and if you don't need its chemical formula for any reason, for instance, to find the molar concentration, we don't even have to look it up if we know what the Kb is. So you could look up the formula for pyridine, but there's really no reason to do so. We can just write pyridine plus water. And in this equilibrium with a weak base, the pyridine is going to take a hydrogen away from the water, and so that'll be pyridine with an extra hydrogen with a positive charge, and we leave hydroxide behind, so that's got a 1 minus charge. So the chemical formula is actually not necessary to helping us answer this question. What I'm going to do is set up a little ice table for us. I'm just going to use the equation itself to help me set up the ice table. So let's see, we've got initial change and equilibrium concentrations. We know we're not going to include water since water is a liquid, so I'm going to cross that right out. And we're interested in the concentrations of the other things here in order to help us solve the problem. So the difference, as I said, when we're setting this up, like with any weak acid or weak base problem, we're dissolving the acid or base in water. There's some initial concentration, and we start off with 0 ionization or dissociation at the beginning of the question, but we don't know the initial concentration. That's what we're solving for. So we're going to give that a variable for now since we don't know what it is. I'm not going to use x since we've been using x for our change line, so I'm just going to call this concentration y. When the pyridine dissolves in water, that initial concentration is going to go down by some value, and the concentration of the ions is going to go up by the same value. So the ratio is 1 to 1 to 1. And at equilibrium, the concentration of pyridine will be the initial concentration minus x, the concentration of the conjugate acid of the pyridine will be x, and the concentration of hydroxide will be x. So this is kind of neat. Like I said, we're going backwards. We can find out what x is in this problem since we know the pH, and if we know pH, we know the concentration of hydroxide. But before I do that, let's just write out our Kb expression so we've got that ready to go. So for this reaction, Kb is the concentration of the conjugate acid of pyridine. Let's just fix that a little bit. Times the concentration of hydroxide divided by the concentration of pyridine. And we do know what Kb is, 1.7 times 10 to minus 9. And we've got in the numerator x times x is x squared, and then in the denominator y minus x. So as I said, we know what x is in this question because we know the concentration of hydroxide once we have this pH. So the pH is 8.5. That's given in the question. If we want to find the concentration of hydroxide, we can find that easily if we have POH. So POH is going to be 14 minus the pH, so minus 8.5. So what is that? 5.5? 9, 10, 11, 12, 13, 14. Yep, so the POH is 5.5. So the concentration of hydroxide is 10 to the minus POH. So that's our inverse log function. So 10 to the negative 5.5. So we'll have to figure out what that is. And then we'll be able to sub that x value into the equation and solve for y, which is what we're looking for. So actually, math-wise, it's not too bad of a question, but the thing is, you have to know sort of how to get what you need from the given information. Okay, and it is weird in the ICE table to have all unknowns. So I'm going to do 5.5 negative, and I'm going to do a little inverse log, and I get 3.16 times 10 to the minus 6 moles per liter for my concentration of hydroxide, and the concentration of hydroxide at equilibrium is equal to x. So that value is going to be equal to x as well, minus 6. Alright, so we have a little bit of what you could call annoying math to do here, but it's not too bad. So 1.7 times 10 to the minus 9, we can multiply that by y minus x, which is 3.16 times 10 to the minus 6, and that is going to be equal to x squared. 10. It's getting a little ugly. 10 to the minus 6 squared, and we will be solving for y here, so 1.7 times 10 to the negative 9y minus, lost my calculator, so 1.7 exponent minus 9 times 3.16 to the exponent minus 6, and what is that? Oh my, 3, 6, 9, 12, 15, so 5.37 times 10 to minus 15, and that's equal to this number squared. So I get 9.99 times 10 to the minus 3, 6, 9, 12. Alright, so we're solving for y. 1.7 times 10 to the minus 9y equals 9.99 times 10 to the minus 12 plus 5.37 times 10 to the minus 15. Whoop. Things are getting a little ugly over here. Plus, okay. So once I add those numbers, I almost get the same answer. I almost get 9.99 times 10 to minus 12, but it actually does round to 1.00 times 10 to the minus 11. So y is equal to that number divided by 1.7 times 10 to the minus 9. So 1 then I get for y, I get 5.9 times 10 to the minus 3 as my answer for y. So my initial concentration of pyridine in this question is 5.9 times 10 to the minus 3. So the initial concentration of pyridine is 5.9 times 10 to the minus 3 moles per liter. Okay, so that's what we were looking for in this case. Definitely a lot of ugly math with exponents over here, but it's actually not too bad. And it's possible, it's probable here, that we actually could have ignored the x. So we could probably have made the assumption, since KB is very small, that we could ignore the x in the denominator. So that's something you're welcome to try out if the x is small. You can retry this question if you would like, assuming that you can get rid of that x and see if you get the same answer for y. We're looking at questions now in section 8.3 in your text with base equilibrium, so give them a try.